Right. So now what we want to consider, now that we have dealt with microcanonical ensemble, now typically microcanonical ensembles are the one which refer to the isolated system in the language of thermodynamics. But isolated systems are very, very rare in real life. Normally, we always see that our system is either in the presence of a heat bath, the reservoir all around us, either in a thermal reservoir or is connected to the open air, therefore there is a barostat that maintains the constant pressure in the system, so on and so forth. So essentially, we always have system plus a bath. Now this bath can regulate temperature, can regulate pressure, for example, I can keep a small container and leave it outside. So let's heat up the container. There is a liquid or a gas which is contained in that container. You heat it up and you leave it outside, and you come back after a day. You will see that the container has the same temperature as the outside temperature. So essentially, the whole environment surrounding this container acts as a bath. I can also leave the container open, in which case the pressure in the container is kept constant and is equal to the atmospheric pressure P0. So a bath is typically a heat reservoir, or essentially the other languages it's a reservoir that can be used to maintain temperature and pressure. Now such a system, when it is connected to a bath, is what is statistical mechanics. It's called a canonical ensemble. So in the first canonical ensemble that we considered, the possibilities are that, of course, I will keep the temperature fixed, which means only energy exchange is allowed, right? So the system, and I want to find out the probability distribution of the density for the system to be in the energy state E. The system has an energy E, and it's connected to a bath which has an energy, let's say EE, the environment, so that the total energy EE plus E is a constant quantity, right? Now probability that system has energy E is equal to the probability that the reservoir or the bath has energy ET minus E, right? Therefore, we write rho of E, which is the probability for the system to be in the energy state E, as proportional to the total number of microstate of the bath with the energy ET minus E. However, also note that energy being an extensive quantity, the bath is so large, the reservoir is so large, that in this equation the dominance is of this energy EE. So what we will do as our next step is we will approximate this as EE minus E, right? Therefore, so E, since E is negligible, is small, one can clearly approximate this to minus E del omega B del E evaluated at E is equal to EE, plus higher order terms, which we'll ignore because E is so small. So again, just very briefly to say that I have a system which is connected to a bath and which is allowed to exchange energy, right? So the system's energy can actually fluctuate. Now But the total energy, which is E total and is a sum total of EE, the energy of the bath plus the energy of the system. You should note that this bath plus the system is a microcanonical ensemble. And therefore, the bath is so large compared to the system, the probability that the system has an energy E is the probability that the bath has the energy E total minus E. Now, the bath is so large that it itself is like an isolated system, and therefore this probability, or rather the right hand side, is proportional to the number of microstates accessible at energy Et minus E, right? So then I have rho of E is equal to this. If I take a log of this is proportional to, now is going to be, but well, before I take a log, I want to just simplify this a little bit more so that I can write down this as proportional to omega B E of E 1 minus E 1 by omega B del omega B del E plus higher order terms. So this becomes omega B EE 1 minus E del ln omega B del E plus higher order terms. This is my probability of finding the system in the energy state E. Therefore, if I now take a log of E, this becomes ln omega B E plus ln 1 minus E del ln omega B del E plus higher order terms. But del, so first note that ln omega B is S over Kb, right? It's the entropy of the reservoir, because the reservoir is so large, the reservoir plus the system both totally is, this acts as an isolated system, and one can apply macrocanonical ensemble to this system plus reservoir. But since the reservoir is so large and the bath is a tiny fraction of the reservoir, is small, therefore I can use this expression. So then this becomes ln omega B EE plus ln 1 minus E del S B del E, right, plus higher order terms, which would then approximate to, not approximate to, which will rewrite to 1 minus E del SE over T. And this T is the temperature of the bath, not the system, right? Good. I can expand the log omega B times EE minus, sorry, this has to be S over KBT, right? E over KB minus E over KBT. Note, this is the temperature of the bath, right? So that rho of E is a constant we will call A e to the power minus E kBT. So the probability of the system to be in the energy state E is given by this expression. The A is obtained from the normalization. So if I just do sum over rho E, which is going to be 1, which means A e to the power minus E over kBT. But what am I summing over? I am summing over all possible microstates, right? And rho of E takes the form 1 by Z e to the power minus E over kBT, where we have written Z as sum over all possible microstates e to the power minus E over kBT, right? This, I mean omega E, one can also write as this, where omega E is the number of microstates with energy E, and sum over E. If you want to look at in a continuum way, then this is going to be dE omega E e to the power minus e kBt. Depends on the system you are looking at, and omega E dE is the total number of microstates between E and E plus dE, right? This is what is called a canonical distribution function, right? And we shall work with it. The central quantity of interest is this one, Z, which is called the partition function. In canonical ensemble, the whole trick is involved is to evaluate this partition function, right? But all of this is fine. So all of this has been derived from the fundamental postulate of statistical mechanics, that you started off with an isolated isolated system. You use the principle, the language or the work, I mean the theory that we did for the microcanonical ensemble. You use that thing and then essentially determine the probability density for the system to be in the energy state E, right? Now the biggest part is I have to make the connection with thermodynamics. Now to build the connection with thermodynamics, we note the first thing is that in thermodynamics, the quantities that we have dealt with are essentially quantities which are constant, right? For example, the energy U, which is equivalent to E in our description, in the statistical description of a system, is a constant over time. These are macroscopic quantities which show no fluctuations. Correct? But clearly, what we have over here is the energy of the system fluctuates because we are describing it in terms of a probability density, right? So how do we bridge the gap, or how do we make the connection? The first thing that we note is that the internal energy that we had in thermodynamics is identical to the average energy in statistical mechanics, right? But the mean or the average is only meaningful if the distribution is sharply peaked, when you have a well-defined mean, right? So for example, if I have a distribution of energy which looks like this, then this is a relevant quantity, then everything is meaningful because you see the width and the distribution, the mean, are well defined. But if I have a distribution which is like this for the energies rho of E, then I am in a little bit of trouble because the width of this distribution spreads all across this range, and therefore range of allowed ranges of E, and therefore the meaning is not the meaning of mean, the average, is not very meaningful, right? So let's see, the average of energy in a canonical ensemble is essentially sum over E rho E, which is 1 by Z sum over E to the power minus E over kBt, and the sum is over all state. So now let's take a derivative of this average energy with respect to temperature. Then the first term is sum over E to the power minus E over kBt del T of minus E over kBt plus sum over E to the power minus, well, we'll put it later on, let's say. So we write this as minus 1 by Z square minus 1 by Z square dz dt sum over dt, capital T, sum over e to the power minus e over kbt, which is equal to 1 by z sum over e square over kb t square. This is comes from the derivative e to the power minus e over kbt minus 1 over z square dz dt sum over e to the power minus e over kbt. Now z, the partition function, is sum over all states e to the power minus e over kbt, and therefore dz dt, if I take a temperature derivative of this partition function, is sum over e to the power minus e over kbt del t of minus e over kbt, which is again sum over e over kb t square e to the power minus e over kb t, right? So our expression for del E del t is equal to one over z. Let's first take out 1 over kbt square, then 1 over z sum over e square e to the power minus e over kbt minus 1 over z square 1 over kb t square, and then I have dz dt, which is going to be sum over e to the power minus e over kbt, then another sum over e to the power minus e over kbt. 1 over kbt square, this you clearly see is the average over e square minus, if you look over here, I can now take the z square and write it like this. But this is average over e, this is average of e, so that I have average e whole square with a bracket outside. So therefore this quantity is delta e square average is equal to del et del t. So that, but this quantity on the left hand side is nothing but the specific heat C. So I have kBT square times C is equal to delta E square. So delta E square of this divided by average of E is going to be kBT square C, not kb square but kBT square, times C divided by average of E. This is the term which is not very interesting to me, but it's this ratio which is important. C, sorry, this is wrong. Since I have taken the square root, this is going to be square root kb t square square root c over average of E. It's this ratio which I'm interested. Now C, which is identical to del E del T, is an extensive quantity, and therefore it will scale with n. So square root of C, the specific heat, is going to be square root n. In contrast, average of E is going to be scaling as n, right? It's an extensive quantity. So therefore delta E square over average of E, which is essentially the ratio of sigma over the mean, the standard deviation over the mean, is going to be square root n over n. So we will just write down this, will go as 1 by square root n. Now this is a remarkable result. Essentially that tells you that if you keep on increasing the number of particles in the system, your distribution of energy, which is a fluctuating quantity in the canonical ensemble, becomes sharper and sharper, so that the sigma over mu will scale as 1 over square root n. It's a consequence of what is the central limit theorem. because the total energy is essentially sum total of energies of the individual particles, which are itself random, right? Now, what do we do next? Well, we take the partition function and we write down. Now, the first thing we have cleared off is that, look, in our description, in our statistical description, is clearly meaningful that this expression that we have derived and all the derivations that we have done, starting from the fundamental postulate of statistical mechanics, which is S equal to KB ln omega, is really meaningful, because in a sense what I am getting it at is that if I, in the thermodynamic limit, where I really have a large number of particles in the system, my distribution becomes sharply peaked. So the mean is truly meaningful, and this average I can connect to the internal energy in thermodynamics. But we have still a little more to go. So let's look at let's start again with the partition function, where this was all over all states, e to the power minus e over kbt. So we start off with the partition function, where I have z as the sum over all states, e to the power minus e over kbt, and which we write dE omega e if there is the energy states are a continuum, e to the power minus e over kbt. So that this integral is dE e to the power s over kb e to the power minus e over kbt, which is integral dE e to the power minus e minus ts over kbt, right? Now note that e minus ts is an extensive quantity, because e also scales with n, s also scales with n. Therefore this quantity is an extensive quantity, that scales with n. And therefore in the thermodynamic limit we can use the saddle point to evaluate this partition function, right? Which would mean that we minimize e minus ts, right, del e of this, to give me the minimum energy, or to the energy at which the system is likely to happen is going to be 0, right? So this means that T del S del E at E is equal to E bar is going to be 1, which gives me the thermodynamic relation that del S del E is going to be 1 by T, correct? Now once I have this E bar, I want to write down this part in terms of this. So E minus Ts is E bar plus E minus E bar. So what I'm trying to do over here is I'm trying to write down this argument of the exponential around this energy E bar. Minus E bar minus T of SE minus T del S del E evaluated at E bar times delta E minus T by 2 del 2S del E2 E bar delta E square plus higher order terms, right? So that I have E bar plus this 2 makes it delta E. So here the delta E that I have used is E minus E bar minus T of S E bar minus T of del S del E evaluated at E bar minus T by 2 del 2S del E2 E bar delta E square plus higher order terms. Let's take the term constant for T minus S E bar. That's the first term that I have. So there is a delta E over here, so I can group that with this delta E to write down T del S del E at E bar times delta E minus T by 2 del 2S del E2 evaluated at E bar delta E whole square plus higher order terms. Good. This term vanishes because of this condition that we have just derived, right? Because E bar is given by this. So I have E bar minus T of S E bar minus T by 2 del E of 1 by T. Since del S del E is 1 by T times delta E square. Correct? So we'll call this F, this quantity, minus T by 2 minus 1 over T square del T del E delta E square, right? So I have F bar minus, this becomes plus, this becomes 1 over 2T del T del E. But del T del E is essentially inverse of the specific heat. So I can write down, so there is a delta E square over here, of course. I can write down this as F bar plus delta E square 2TC, the specific heat, right? So del T del E is equal to del E del T inverse, rule of partial derivatives if you recall, and this is 1 by C. Good. So therefore your partition function Z is e to the power minus F bar over kBt integral over d of delta e to the power minus delta E square over kBtc, right? Is this correct? Let's just see. Sorry, there has to be a T square over here. So that ln of Z is going to be minus F bar over kBt plus log of this integral d of delta e to the power minus delta E square over twice kb t square c. But this integral is a Gaussian integral, and if you evaluate this integral, you are going to get a term which is going to depend only on c. Therefore, this whole term is of the order of log of n. In contrast, if you see over here, this term is of the order of n, because this term by definition is E bar minus Ts of E bar. Right? This is extensive, therefore this quantity is also extensive. So in the thermodynamic limit, essentially what we will have is ln Z, okay, let's just write it down as F bar over kBt plus, if you look at this, if you integrate this, then this is going to be ln square root of n. So in the thermodynamic limit, there is going to be some factor, but we will not worry about that. But it's just, well, we'll just write down this as a times ln n square root n to be correct, where a is to be determined after you evaluate this integral. But in the thermodynamic limit, this you can ignore compared to the first term. This term you can ignore compared to this term, so that you have F bar as minus kBt ln Z. And this quantity we have already encountered, E minus Ts, we have already encountered in thermodynamics. If E is identical to your E bar is identical to your internal energy, and S is the entropy, therefore this is the Helmholtz free energy. So once you calculate the partition function Z, you calculate the route to thermodynamics is provided by this relation. You first calculate the Helmholtz free energy F, and from there you calculate all the quantities that you need. For example, once you know F is E bar minus Ts, right? So let's just see. So now we will remove the distinction between bar and this. We will just say that F is E minus Ts, right? What is average
of E. The E, which is, okay, let's put the bar so that it's understood. Average of E is sum over e to the power minus E over kb t, correct? Now sum over all states. Is it possible to manipulate in terms of the partition function? That is all one has to figure out. So if this, I can write down sum over del t of e to the power minus E over kbt. But then this, if I do a del t, it's going to get me an additional 1 by t square. So I have to multiply this by kb t square. If you don't believe me, then you can explicitly do this. We have done this earlier. It's going to be e to the power minus E over kbt times minus E over kb del t of 1 by t times kb t square. Okay, so let's write it down properly. I have 1 over t times kb t square. So this is sum over e to the power minus E over kbt 1 over kbt square times kb t square, and then I have basically this as the average of the energy identical to E bar, right? So this is the expression I have. Now from this I can pull out kbt square outside, E bar as kbt square sum over, I can take out the derivative also, del t of e to the power minus E over kbt, where the sum is over all states again. But this is the partition function. So essentially you have 1 over kb t square del t of z, right? So this quantity is minus kbt ln z, the Helmholtz free energy, the left hand side, and this is kbt square del z del t minus ts. So I can divide throughout, sorry, kbt square, I can divide throughout by temperature to give me S is equal to kbt del t of z. Okay, I'm sorry, I have missed one thing. There has to be 1 by z.